All right. Well, everybody have a good Labor Day?
Yes.
Did you labor?
No.
No, neither did I. Well, I did a little bit. Anyway, one of the things that I did over the Labor Day holiday was to grade your first assignment. So did you guys get, now I checked on my previous class and apparently Courses is working good with the notification. So did you guys get notification that I graded your homeworks? You didn't get notification? Email? Shoot. But some of you guys did.
Sounds like everyone else did.
Yeah, well, maybe I forgot to check the little box on yours when I downloaded to Dropbox. But anyway, check Dropbox
Yeah.
and it's there. So any questions about that homework that you got back or anything, or up till now, that we've done up till now? So it's been a few days because of the holidays since we last met, and so let's just go over real quickly what we had introduced this concept of tail recursion. And remember, we said that our author uses the word iteration. And what did we say that another word for iteration is? When our author says iteration, what does he mean?
Tail recursion.
He means tail recursion. Yeah. That's another word for tail recursion, or tail recursion is another word for iteration. And why did we say that he likes to call tail recursion iteration? Iteration is normally what kind of a programming construct? It's a loop. So why does he like to call tail recursion iteration? Because what can happen behind the scenes?
Compiler can convert it from one to the other.
Yes, a compiler can convert a tail recursive algorithm behind the scenes into a loop. So if you write a tail recursive function, when it executes, it's actually not calling itself over and over and over again. Even though it looks like that's what you wrote, because the compiler can turn it into a loop. So here's tail recursion. What our author calls iteration is more commonly called tail recursion. A good optimizing compiler can convert a tail recursive program into an iterative one as a loop. And we said, now do you remember how to recognize something that is not tail recursive? How do you recognize if somebody shows you, say, hey, I got this great recursive algorithm. What do you look at to see, is it tail recursive or not? What do you look for?
If after the recursive call has to compute something.
Yes, exactly. After the recursive call, if it has to do some more computation, then it's what? Not, well, it's not tail recursive. So, right? So, and the example that we gave was this n factorial, n times n minus 1, and the reason it's not tail recursive is because after we call the n minus 1, we got to multiply it times n. Right? And here was the general idea. The general idea is that the function calls the helper function once. And then the helper function is tail recursive, and it calls itself tail recursively. Right? Now, I kind of think that we were I'm just trying to remember where we ended last time. The helper function has an extra parameter, and the extra processing is done in the parameters of the helper function. Now, is this where we were?
Kind of like starting.
Did we actually program a tail recursive function? I should have reviewed my.
We ended right.
I think we ended kind of pretty close to here, right?
We already talked about the 1 and n.
Yeah. I remember, I think I was it was like pulling hen's teeth to get you guys to come up with the helper function with two parameters a and b that computes a times b factorial. If you have a function that computes a times b factorial and you want the function to return n, how do you call the function? What values do you give a and b to make n factorial come out? 1 and n. Why is that? So here it computes a times b factorial. So if you give it values a equals 1 and b equals n, then what's it computing? It's computing 1 times n factorial, which is n factorial. Remember? I think, is this the one that we kind of like struggled with a little bit? So here, so now what we're going to do is the helper function is going to be a times b factorial. But now, what is a times b factorial recursively? Look at this. What is a times b factorial recursively? On factorial, right? Now look, do you see that there's no extra processing that has to be done after you return from the tail recursive function? Do you see what you see how that works? You don't see how that works? Do you agree that a times b factorial is a times b minus 1 factorial? That is mathematically valid. Yeah? That's a mathematically valid expression. But look, you guys, do you see that on the top there, do you see that the n minus 1 factorial is the recursive call? And then after the recursive call, you have to multiply it times n. But now do you see that if something computes a times b factorial, the recursive call would be what? What will in place of a, what will the recursive call have in place of a? A times b. And in place of the b factorial, what will the recursive call have for b factorial? B minus 1 factorial. And after you make that call, do you see that there's no more processing that needs to be done? No more processing that needs to be done. Compare this expression up here to this expression down here. No, I know, but look. Do you see that up here, if you were to program this, n minus 1 factorial would be the recursive call. After the recursive call, you'd have to multiply that times n. Yeah? No, that doesn't happen after the call. That happens in the parameter list of the call. Because you see the helper function doesn't have one parameter, it has two. Look, go back here, look. The helper function has an extra parameter. That's why we need the extra parameter. The helper function has an extra parameter. The extra processing is done in the parameters. So you see, it makes all the difference in the world that this whole thing is the one recursive call. And after that recursive call, no more processing. Are you with me? Because look, what will the helper function do? What will the helper function compute? It will compute a times b factorial, right? It will compute a times b factorial. So it's going to have two parameters.
Could you clarify what a helper function is?
Yes. Yeah, well that's yeah, here, let's go back. Let's go back and look. It says, the function calls a helper function once. See, here's the factorial function is going to call the helper function once. What it's going to do is, you see, the helper function is going to compute this. So factorial is going to call it with a 1 for a and an n for b, and therefore it will return n factorial. Okay, so it's going to call the helper function once. With two, it's going to call the helper function once with 1 for a and n for b. Then the helper function is going to call itself tail recursively.
What is a helper function?
It's an additional function,
Okay.
and we're going to name it like we'll give it a different name, and it'll have two parameters. And these are the characteristics of a helper function in tail recursion design. Okay, what happens is we have an additional function. So the function calls a helper function once. The helper function is tail recursive and calls itself. The helper function has an extra parameter, and the extra processing is done in the parameters of the helper function. See? So look. So what happens is this. So in this particular example up here, this is the recursive call. After the recursive call, it multiplies it by n. But now with this one, this whole thing is the one recursive call. You see the difference? I mean, I'm trying to get you to see conceptually before we dive into the code. Conceptually, what happens is there's only, no processing has to be done after the recursive call, because what it computes is a times b factorial. But recursively, a times b factorial, it's going to call it once. What's the recursive call going to be? It's going to have what for the first parameter? A times b, and what for the second parameter? B minus 1. You see what I'm saying? So the main function calls the helper function with a value of 1 for a and n for b.
And then at the end of the computation, the helper function just returns that.
Yeah. Well, it returns a times b factorial. But because it was given 1 for a and n for b, it will be returning n factorial.
So n factorial is stored in a at the end.
Nothing in functional programming, nothing is stored anywhere. In functional programming, it's returned. The thing.
A refers to the value of a times b factorial at the end of the recursive call.
The last one.
Yeah.
Yeah, at the end. Yeah. Question?
Does the tail recursive function always have 2 parameters?
It usually has one more parameter than exists in the original function. That's kind of like the programming technique or the idiom that you use. That's the way it normally works. Question?
Word was clear. I'm just still confused. So the helper function is the a times b minus 1 factorial part?
The helper function is going to have two parameters, a and b, and it will compute. So it's going to have two parameters, and it will compute a times b factorial.
Which one? What is the helper function? Yeah.
It's an additional. It's a function that we write in addition to the original factorial function. What we're doing is we are rewriting our factorial function to make it tail recursive, and in order to do that, we have to
Do we have the helper function written there somewhere? Is one of them?
No, I'm going to show you. I just want to get you. Yeah. Sorry, no code yet. I just want to get the idea. You got to get the idea. Try to get the idea before we. Actually, we'll dive into the code right now. Okay. So let's write factorial now, and the helper function is going to be called. What does it look like here? Helper function is going to be called what? Factorial product. And how many parameters will factorial product have? 2. How many parameters does factorial have? 1. Yeah, question, Chris?
The helper function, do we only utilize that when we evaluate the functions that are factorial? Is there other functions that we...
Now, we are going to write the factorial function to be a tail recursive function to help us compute factorial tail recursively. And yeah, I'll say some more general comments afterwards. Okay? So, all right, so now let's go to our demo. Okay, so here's our demo. Now, I guess you could write these in any order, but I think it might be better if we write the factorial first. So how do we define factorial? Parentheses, define factorial. All right, and what do we always put on the second line? Lambda. All right, and now, okay, and here we go, you guys. How many parameters does factorial have?
1.
It has 1, right? So let's call it n. Are you with me? And what did we say factorial is going to do? Yes, and what did we say the name of the helper function was going to be? Factorial product. So here it is. It's just one call. So what are we going to return? Actually, you know, what goes here is what gets returned, right? Okay, and so what are we going to return? Factorial product. But now, here's my question. Factorial product has how many parameters? It has 2. And they are what? They are, remember it was on the slide, we called it A and B. But what did we say we were going to call it? We were going to call it with a value of what for A? 1 for A, and what for B? N. And now look, that's it. There's our factorial. Of course, we haven't written factorial product yet. That's going to be the hard part. But now, does everybody see that that's what, and actually, you know, you can actually compile this even without factorial product being, see, look, it didn't complain that there was no factorial product. It won't complain until we try to run it. In fact, here, see, now, if we do factorial 5, now it will complain, see, undefined, because it actually tried to run it. Okay, so now we need to define factorial product. Okay, so here we go. Define factorial product. Okay, and what always goes here? Lambda. But now, how many parameters does factorial product have? 2. So let's put, and so let's call them what we call them in the slides, A and B. And here, let's put a little comment here. What does this return? Let's put returns. So what does this return? Remember what we said it returned? What does it return? No, it doesn't return 1 and n, because 1 and n is what we're calling it with. But what did we say it returns? No, it doesn't return n factorial. That's what, actually here, let's do this. Here, let's do this. Let's do this. Returns, this is what returns n factorial. But what does this return? This returns a times b factorial. Now, is everybody, are we starting to get it now? This returns a times b factorial. Are we good? You guys? Now tell me, let's go back to our what did we say? What did we say here, you know, on our slide here? What does it say? What is it that we're computing? We're computing a times b factorial, right? Now, what's going to be the base case for this? Yeah, if b equals 1, let's look at this expression. If b equals 1, then what is b minus 1? 0. And what's 0 factorial? 1. And then what's a times 1? A. And then what's that a times that 1? A. So what should we return? Let's go back. So what should we return in our, here in our, if what? This is our base case, right?
If B, oh,
Yes, good. If what?
is it like equals
Yeah, paren equals,
0?
B, 0. Okay, boom. And now, what happens if that's true? What do we return?
A.
We return A. Yes. Excellente. Now comes the recursive call. Otherwise, what do we return? Do we have to do like times something, or do we have to do, plus something? No. Because this is tail recursive. So what do we put? Yeah, we return factorial product. Are you with me? You see how this is going to be tail recursive? So we return factorial product, but it's factorial product of what? Now we're going to have 2 parameters, right? And what's the recursively? What did we say recursively a times b factorial?
A times b times b minus 1 factorial.
Yeah, exactly. So what's our first parameter? Times what? Yes. Times AB. All right? That's the first parameter. And what's the second parameter? Yeah, excellente. Minus B1. Boom, 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 boom. There it is. Let's compile it. It compiled correctly. And let's try factorial 5. What was 5 factorial?
Should be 120.
Ta-da! It is 120. Now, do you see why this is tail recursive? It's because factorial product, look what factorial product does. This factorial product here, in the recursive case, it calls itself, and after, oops, got all these. It calls itself, and after it calls itself up here, it doesn't have to do anything else. It doesn't have to add anything. It doesn't have to multiply by anything. It doesn't have to do quotient. It doesn't have to do anything. So that's tail recursive. And so when I ran that, it wasn't really calling itself over and over and over again. Behind the scenes, it was in a loop. Yeah.
So basically, if you just call it and all of the like operations, I guess, are within the call of the function, then you're good. It's still recursive. If they're like outside the call of the function or not.
Yeah, I think what you said is true. Say that, ask the question again.
So if you
If-
have operation, like if you have your operator before you call the function, it's not tail recursive.
Correct. That is,
But within the call of the function, it is.
that is correct. So notice, and the reason this is tail recursive is because after we call factorial product, we don't have to do anything else to it. So there, mathematically, there is a way to convert this tail recursive call into a loop with no runtime stack. You can kind of see why you can do that. Because if you have any processing outside of the factorial, outside of that, that has to all happen that has to take place on the runtime stack. Yeah? Is everybody good? Okay. Now guess what we're going to do? Now guess what we're going to do? We're going to prove that factorial product is correct. So now let's go back and review those. Remember how we had to prove something is recursive, something is correct? What's always the programming technique that we use? Yes, proof by mathematical induction. Because the base case of the function call refers to corresponds to the base case of the proof by mathematical induction, and the recursive call corresponds to the induction step. Okay, so there's the code that we just entered and tested. But of course, testing doesn't prove anything. Who knows? If we had tried it with 6, it might not have been correct. So what are the two? So here we go. There's the code, and here's the base case. Now, do you remember how we do the base? Do you remember how we do these proofs? We always have, on the one hand, we have something, and on the other hand, we have something else. So what do we have on the one hand? We have the code, and on the other hand, what do we have?
Math.
The math. If these mathematical functions are trying to prove correct, we want to compare the code with the math. And what do we always start off with in the base case? We always start off with what?
Code.
Yeah, the code. And what do we call it? Code inspection. We inspect the code, we see what it returns. Yeah? Okay, so here's the base case. So what's our first thing that we do? Okay, what's the base case here? It's in the code there. It says equals what? If what?
B equals 0.
Yeah, if equals B0. Yeah, so if B is 0. So the base case, and what do we see by code inspection? What does code inspection tell us?
That it returns A.
Yeah, exactly. Code inspection. Factorial product A0 returns A. Are you with me? So there's the code, and then now what do we have to compare that with?
The math.
The math. So what expression do we have to evaluate mathematically? Yes, we have to compare that with a times 0 factorial. So the math says a times 0 factorial. But what is a times 0 factorial by math? That's a. So a. Therefore, what? Boom. Yeah, therefore, boom. Correct in the base case. But now, what about the induction case? What do we have to do? And with an induction case, what do we need, assuming what? We need to prove what? Yeah, something, assuming what? Something else as the inductive hypothesis. And how does that always work? So what is it that we, so tell me, what is it? Here's the inductive case. So can you tell me what we have to prove and assuming what as the inductive hypothesis? How would you set this up? Eh? Testing, 1, 2, 3. Is this mic on? I don't hear anything. You hear the question?
The factorial product.
Yeah, come on, help me out. I'm stuck. Yes, we prove that factorial product x. Oh, this is going to be a little bit different from what you're used to. We're going to assume that factorial product xb terminates with value x times b factorial. You'll see why I'm using x instead of a here in a minute. But now that's what we have to prove, that factorial product xb terminates with value x times b factorial. But assuming what as the inductive hypothesis?
X times b minus 1.
No, not times b minus 1.
Factorial times b.
Huh? No, wait. What is it? What is our specification here? What does it say up here? A times b factorial. So what do we want to, we want to prove that this terminates with this, assuming what?
The factorial product returns a times b factorial when b is greater than or equal to 0.
Assuming b factorial is equal to,
Now, how do you assume it for n, assuming what?
Factorial product x b minus 1.
Yeah, assuming n minus 1. Is everybody with me on this?
You said back 1 from x to b.
X can be just any old variable you want. X can be any expression you want. But the main thing is you want to prove that it works for b, assuming that it works for what? B minus 1. So here's how you formulate it. Assuming that factorial product y, parentheses minus b1, terminates with value y times b minus 1 factorial as the inductive hypothesis. I'll make these slides available eventually, but just we haven't finished chapter 3 yet, so I haven't posted them yet. Now look, here this is a little tricky, because look here, you guys, this x corresponds to this x, but it can be anything. So to emphasize that it can be anything, I put a y here, and this y is the same as this y, and it does not have to necessarily be the same as this x right here. Because our induction is on what variable? This is by mathematical induction on what? On b. Are you with me? We actually have two variables floating around here, a and b, but when you do a proof by mathematical induction, you always prove it on one of the variables. That means that this first variable can be anything, as long as this is this, and this is this. This doesn't have to be that. Same as that. Now, does everybody buy this? Because look, if we can prove that this is true, assuming this is the inductive hypothesis, then it's also n plus 1 will be true based on n, and then n plus 2 would be true based on n plus 1, and so on. Okay, so that's how it goes up the ladder. So what's the first thing that we start with? What's the very first thing that we start with? Yes, what it returns. That's exactly right. So here's the inductive case. The value returned by factorial product AB. Now, and what's this always this first step? Give me what's the hint on the first step? Code inspection. Let's inspect the code. Dun, 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 dun. What does it look like it returns? It returns this. Yeah? So, equals by code inspection, factorial product, blah, 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 blah. Right? But now look, you guys, what does the inductive hypothesis say? Let's go back to the inductive hypothesis. What does the inductive hypothesis say? It says what? It says this returns what? This times this. Are you with me? So, therefore, this equals by what? By the inductive hypothesis. Now, what is it equal by the inductive hypothesis? A times B.
B minus 1.
Times factorial. So A times B minus 1. That's by the inductive hypothesis, right? But now we do some really trivial math. What's the trivial math? Yeah, good. Math. That's good. Good. So, but now what's the math?
A times B factorial.
Well, it's A times, and then,
B times B minus 1.
yeah, that's, what law is that? Associativity of multiplication. And now, by what? By some more math. What's B times B minus 1 factorial by math? B factorial. So that's A times B factorial, and we're done. But it's the same setup. All right? This is like the second or third proof now that we've done, right? So it's always the same setup. You got the base case. You prove that the base case is true by comparing the what with the what? The code inspection with the math. And then for the inductive case, you set up what you have to prove and the inductive hypothesis. You start with what it returns. By code inspection, you see what it returns. By the inductive hypothesis, you plug it in and boom. All right? So, you know, there's no higher math involved here, but it's higher logic thinking. I mean, you know, you got to just get all the pieces in place there. Okay. So, now let's do another. That was our first tail recursive example. Now let's do another tail recursive example. So the next function we're going to do is the power function. So check this out. So here's the power function. We want to write power 4, 5. So now that should return 1024. Why? Because what? Yeah, exactly. Because 4 to the 5th power is, so that's 4 times 4 is 16 times 16. Wait, how does that work? Oh, wait, it's 2, 4, 8, 16. Oh, no, that was powers of 2. It's 4 times 4 times 4 is 64 times 4 is 256 times 4 is 1024, right? Okay, so power 4, 5 returns 4 to the power 5. Yeah, so that's what we want to write. Only thing is, we want to do it tail recursively. So now, how would you do it not tail recursively? Look. What is b to the e? Not tail recursively. What is b to the e? B times b to the e minus. But do you see then that this b to the e minus 1, that would be the recursive call. And then what would we have to do after the recursive call? Multiply that times b. So what do we know about that? Oops, that's not tail recursive. So now let me ask you, can you come up with the tail recursive way to do this? What do we, tell me, see if you can. The base case in this one is e equals, in this case e equals 1, it's b. Oh no, sorry, that e is not the e, oh yeah, no. This e means exponent. It does not mean the base of the natural logarithm. Oh, that would be confusing. Oh, no wonder, no wonder. Okay, yeah. No, sorry. B is the base, e is the exponent. Sorry. Maybe I should have used a different letter, but it's too late now. So now, how would you write this? We're going to have a helper function. By the way, how many parameters does power have? It has 2. What are the parameters? B and E. But now what will the helper function have? How many?
3.
It'll have 3. Yeah, how are we going to, and how's it going to work? Can you?
Two parameters that are both b, and then I'll multiply, and then a third one is like a counter or something.
No, don't think of a counter. Yeah, a counter is, no. Yeah. See that, remember how that's the old procedural paradigm with counters and assignment statements to add up. Yeah, that's what we're trying to get out of. Yeah, anyway, so what do you think?
The first two will be both b.
Well, what do you think it should compute? See, because the helper function is going to compute something different from b to the e. And then we need to write down. See if you can write that down. See if you can. You know how? Here, look. You know how we said. Look here. Know how we said n factorial is n times n minus 1 factorial, and we said this is not tail recursive, right? And then so instead of writing n factorial equals this, what did we write? Instead of writing n factorial equals this, what did we write? We wrote what?
A.
We wrote a times what? B factorial equals what?
A times.
Equals a times b times b minus 1 factorial. And so this is not tail recursive. Here we made it tail recursive. So now what do we have? Look, see, try to do the same reasoning. Now, this is not very dark. So now look. Now what are we trying to compute? What are we trying to compute?
B to the E.
B to the E, and we're saying that it's b times what?
B to the E minus 1.
Yeah, b to the e minus 1. But this is not tail recursive. So now
A times B to the E.
a times b to the e equals what? So now you see it's now we have an a and a b and an e. So now what is this?
A times B.
Yeah, this is a times b times what? B to the e minus 1. And now this one is tail recursive. Yeah.
In the last one, you changed n to b, so does it matter that b is going to be?
Ask that again?
Sorry, does that make sense? Like in the factorial one,
Yes?
instead of writing like a times n factorial, you wrote a times b factorial. Is that
Oh, no, yeah, sorry. The only reason we did this is because we changed the letters in the in the helper function just to keep it straight in our mind.
Okay.
It was just pure convention. It doesn't, the answer is no, it doesn't matter. There's nothing significant about that. But now look, see, now this one is tail recursive. A times b to the e is a times b to the e minus 1. So now you guys, do you guys think we can do this? Can you do this? Now, see if, here, so here, let's write power and power product. So can you do this? Let's go to Dr. Rackett. Now, so, anybody?
Define power.
Good. Define power. Okay. Lambda. Yeah, B, E. Excellent. And what this is let's document it. Let's say this is B raised to the power E. B raised to the power E. Okay? And now what is it going to call?
Power product.
Mm-hmm. Power product. And what is power product going to be? 1 BE. Exactly. And then we define power product, and that's going to be lambda what? Now, how many parameters in power product? 3. ABE. We'll use the same letters this time. And now let's document this one. This is going to be A times B to the E power. A times B to the E power, and that's with E greater than or equal to 0. Okay? And now you guys, what is, so A times B to the E power. So what is our base case? Mm-hmm. So I say if E equals, is that what you said, like this? Paren equals E 0. Oh, wait, what? Oh, if equals E. Oh, should it be? It's A times B to the E power. What is B to the?
Oh yeah, no, 0 is right.
I think it should be 0, right? Because B to the 0 power is what? Is 1, and then, so what should we return? I think it's 0, right?
0.
And then what is that?
A.
Otherwise, what? Now do I have to put times, or do I have to put plus? No, because it's tail recursive. So now what?
Power product.
Power product. Now power product what?
Times AB.
Mm-hmm. Times AB for the first argument, and then what? Same B? Is that good? Or was everybody following? Same B, and then what? Paren minus E1. Paren. Boom, boom. Run. And now let's try. Let's test it. Power. What do you have? 4, 5? 4, 5 should be 1,020. 1,024. Yeah?
When do those 3 terms get multiplied together?
Well, what happens is each time it gets called, A gets multiplied times B. E gets subtracted by 1. And then in the end, when it reaches the base case, A gets returned, and that's it. The answer is never do they get multiplied together. Those 3 things get multiplied together. This does not compute the first one times the second one times the third one.
It just keeps changing A every time.
Well, it keeps it calls itself with a bigger and bigger value for the first parameter and a smaller and smaller value for the last parameter. Are you with me? Until it returns just the A, which is really big in the end. You can look at it that way. Are you with me on that? See, yeah.
Oh, because the other two terms are just there to say how many times you would multiply.
Well, no. Well, what happens is E gets subtracted. You know, actually, that's kind of like the counter that he was talking about. E gets subtracted by 1 each time. And then when it's 0, then A is what we're left with. But A has been multiplied by times B.
Okay, I see.
Yeah? All right. Okay, are we good? All right, and next time, guess what we'll do? Have you heard of Fermat numbers? Well, now that's our previews of coming attractions. Fermat. See you next time.